I'm Brad Booth. I am the president of COBO. That is my volunteer job. My full-time job is a network architect inside Microsoft Azure. And what I'm actually here for at this event is to highlight COBO, the Consortium for Onboard Optics. We recently, in February, released our specification, our release 1.0 of our specification in time for OFC. And we're going around letting people know about it because it is a game changer for how to use embedded optics. Traditionally, embedded optics have been proprietary-based solutions, and we knew that as we progress the technology through the industry, as we move from 10 gig to 40 gig to 100 gig to 400 and whatever speed comes next, the ability to continue to use faceplate optics were kind of presenting greater complexities. One, the thermal environment was getting a little harder to deal with. Signal integrity was becoming more difficult to deal with. The fact that you had people plugging these modules in, which were very sensitive to ESD and sensitive to noise and the damage that you would have from them. And we decided that we needed to start the progression of moving the optics away from the faceplate and closer to the ASIC, if not onto the same footprint of the ASIC eventually. We knew that at 400 gig that it was possible to do faceplate pluggable. We knew in time people would figure out how to do optics embedded with ASICs. But what was going to be the thing that would allow us that transition in between? What would allow us to have the learnings and the understanding to understand how that would change our business models? And that's why we came up with COBO. This is a little COBO module. It's by 16 wide, which means it's a 16-lane interface on this side. And this one was designed for output of 4 100 gig PSM4 signals. This is the medium size version of the module. It comes in a by 8 and a by 16 version, so if you take half of this, you get a by 8 version. It comes in 3 lengths, slightly shorter than this length, and slightly longer. That allows us to be able to use this module literally from multimode fiber all the way up to long-haul coherent transmission. The module in its widest form factor is capable of accepting up to 40 watts of power to drive whatever componentry we need in it. It's capable of having a full 1 RU of heatsink or greater. If we want, you can even do liquid cooling on this if you want. There's the capability of latching either on the high-speed pins or the low-speed pin connector on the bottom. We separated the low-speed power and ground and control away from the high speed to improve the signal integrity. The nice thing is these pins on the bottom are 0.8 mil pitch, which means that we get lots of good contact and power. And these ones are 0.6 mil pitch, which we've done investigation on, which means that they should be able to handle up to 100 gigabits per second PAM4 electrical signaling, which means that this module in its future instantiations will be capable of 1.6 terabits worth of bandwidth. Companies supporting COBO, we have over 60 members. Many of them are very well known in the industry. Guys like Cisco and Arista and Juniper and Mellanox are some of our founding members. We have connector companies, Samtec, T Connectivity, Luxshare, various others that have shown up. We have guys that do optics, actual optical connectors like Senko and Huber-Schuner and Rosenberger. And so we have a collection of everybody within the ecosystem that may have something to do with developing this component or the connectivity of it. And that's one of the things that most people aren't aware of is as we progress, we have to figure out how to move those optics from the faceplate further inside the systems to improve the signal integrity and to enable us to actually get that stuff, those signals out without drawing massive amount of power. And that's one of the advantages of having so many people in the ecosystem that play in this area. We have a lot of good contributions and a lot of information relative to how do we build this. So this module is actually a 4x100. So it's 400 gigs worth of bandwidth in it right now. We know that it can actually, this one today, if you were to build it to handle 400 gig Ethernet, you could put 2 400 gig Ethernets in it, so it would be 800 gigs worth of bandwidth. When this electrical interface goes to 100 gig PAM4 in our next version of our specification, this module will be able to do 1.6 terabit. Is that the endpoint? Probably not, because we've actually designed the module to be able to handle the coherent light, or the 400ZR, which is being worked on by the OIF. That's a 15 watt part, and that does 400 gig per lambda. If the power of that continues to drop, you could potentially put more of those in this and actually achieve even greater bandwidth. The interesting aspect with building something like this and being able to dissipate the power and the heat, the biggest thing for heat dissipation is actually the height that you can get on the heat fin, on the heat sink. So if you get a full 1RU height, you get significantly better thermal performance than just a small one. We've done some general evaluation. We've actually done some thermal modeling. We're looking forward to actually building out true thermal systems and testing this. But one of the key aspects of this is that because you've got a full height and you're not blocking the faceplate with optics, you don't need as much airflow to pull through the system. You don't need those little fans running, full out to be able to pull enough air through to cool it. The other thing is that you can actually change how you implement your design. You could put these modules in a placement in different spots within the system that are potentially cooler or further away from the hotter ASIC. Or you can do channels, airflow channels to cool the optics separate from the actual switch ASIC. There's liquid cooling capabilities that people could use. It doesn't have a heat sink on it right now. You could drop a liquid cooling plate on top of this and liquid cool some of these if you needed to put more power through it. There's also the capability that we have extra pins on the bottom, so we can actually provide more power and more control signals if necessary for some of the next generation technologies. Yeah, so fiber alignment's an interesting aspect with this, is that we expect most people in the first generation will do these with pigtailed optics. In other words, the optics will already be pre-attached. These are shown without them because, this is just a mock-up. We have work going on to actually do a connectorized interface here, and we have some people working on how that would actually be implemented. There's a beauty in that if we can connectorize it here and connectorize it on the faceplate, that means that you wouldn't have to worry about it manufacturing. You could put, in the factory when they build this switch, they could put the optics in, then you could come later after the optics and systems all installed and hand fiber trace it out to the pigtails or to the front faceplate. And that would actually help eliminate the worry if you have to replace this, that you have to unstrand the whole pigtail. So we gave an option for people to actually be able to do both. We discussed that, even short pigtail versions and various other things within our optical connectivity study group. And so, we invite people that have thoughts and more opinions on that to come and work with us on this, because this is an area that we think is going to become critically important as we start progressing towards actually putting optics embedded with ASICs.